Good morning and welcome to Module 14 of Acoustics of Vowel Sounds. This is the fourth or fifth unit of a set of 7 on acoustic phonetics. It's a short course on acoustic phonetics, and we come to the acoustics of vowel sounds. And a little bit of recapitulation here would be in place. Like we started with the introductory session, module 10, and moved on to larynx as the source of voice or source of sound. And then 11 and module 12 dealt with the oropharyngeal chamber as an acoustic filter. Now that module plus this module together will complete the picture as to how speech sounds are produced and how vowels, which are the resonant sounds, and oropharyngeal chamber as a resonance chamber as an acoustic filter has been discussed elsewhere. So the two units combined will give you a clear understanding of the acoustics of vowel sounds, or let me say acoustics of vocalic sounds, which will include a few more sounds. So as explained in some of the earlier units, vowel sounds are plus vocalic and minus consonantal. Plus vocalic, by definition, we have said that before in the earlier units, plus vocalic would mean it has the acoustic field very well organized in the form of phonetics, which means it is a resonant sound. There are resonances in the production of vowel sounds. So plus vocalic, minus vocalic as one feature, and plus consonantal, minus consonantal as the other feature. These two parameters give us 4 major classes of speech sounds. Now plus consonantal, on the other hand, is if it's a non-resonant sound, and it can be noise in contrast with music. Musical sounds are the resonant sounds. So then plus consonantal is generally defined as the low energy sounds, and minus consonantal would then be high energy sounds. So vowel sounds are placed in that box where you can see it is plus vocalic and minus consonantal. It is high energy sound, and the acoustic field is also well organized in the form of phonetics or resonance patterns. So vocalic also implies that it is plus resonant, plus sonorant, and also plus syllabic. Sonority, we have said that before, sonority is the audibility of the sound, how the sound is heard, the auditory quality. And high sonority meaning, it's good to hear, its audibility is fairly good, and low sonority would be not so clear or good to hear. So then we have these 4 major classes of speech sounds, and we are focusing on vowels in this unit. So we go back to oropharyngeal chamber as an acoustic filter, as a selective filter, and we find resonance and filter as the two opposite phenomena. If there is resonance happening, meaning some frequencies are picked up and amplified depending on the size and nature and shape of the air column. And if certain frequencies are picked up, the others are not amplified, not picked up for resonance, then those are obviously filtered out. So it is an acoustic filter, or it is an acoustic resonance chamber. So what we see in this particular slide, the slide before you shows the 3 air columns, because air column, in the earlier unit we had compared the air columns like flute and a trumpet. Flute had a straight pipe, and trumpet had a very complex pipe turning over and over and changing the size and shape of the air column, through its course. The oral chamber is like a bent pipe, bent air column, as you can see in the picture. From the glottis, from larynx to the place where articulation is happening or where the tongue is making, taking a certain position to change the oral configuration. So from glottis to that point, you find this is one chamber, and the resonance frequencies of this chamber, or the frequencies which find resonance because of this kind of an air column, that is F1, the first formant. The second formant happens after that. It is an area, it's the column, air column, just above the tongue, which is modulated and modified by the movements of the tongue. So that is number 2, and that is where the second formant is produced. Then the third formant, if at all it is produced, then it happens between the teeth and the lips, the frontmost air column. Formants are not single frequencies, because as you can see, these air columns are large and not strictly uniform throughout, and therefore these are bundles of resonance frequencies. F1, F2, F3 formants are bundles of frequencies which resonate in the air column as the phonated airstream passes through the oropharyngeal chamber. For this, we had earlier mentioned that Gunnar Fant mentioned this formula and worked out this formula for getting the values of the 3 formants. And the formula is as stated here. F for formant is 2 multiplied by I. I is the number representing the first or the second or the third formant. So I can be 1 for F1, formant 1, can be 2 for the second formant, and 3 for the third formant. And then minus 1, this entire factor is multiplied, you multiply this by what you see in the next bracket, velocity of sound divided by length of the air column 4 times. Average length of the air column, you have to calculate what is the average length of the air column in human beings. The male air column average length is about 17 centimeters or 0.17 meters, and velocity of sound at 340 meters per second. So we calculate F1, F2 and F3 as it comes to 500 Hertz, 1500 Hertz and 2500 Hertz for this kind of a normal natural position of the tongue. Now, the normal rest position of the tongue is the articulatory configuration for a vowel which is heard as which is shwa. The formant for shwa or vowel sound, formants are F1 500, F2 1500, F3 2500. But since the length of the air column, your oral chamber may be different from mine, and each one of us has a different size and length of the air column. Depending on that, it can vary in the male articulation, female articulation and the children's articulations. If you have a smaller air column like women's and children's, then the frequencies are bound to be a little higher. But if it is vowel then what you will mark here is the F1, F2 and F3 will probably be 1:3:5. So that ratio is important. 1:3:5 for vowel whether you have 500 or 700 F1, then 3 times 2100 will be the second formant, and 5 times 3500 will be the F3, and that can happen probably in a child's voice where the oral structure is very, very small. So length of the air column I just mentioned, the X frequencies for male, then it has to be more for females and still higher for children. Now, the oral configuration of different vowel articulations and corresponding formant frequencies can be seen in this figure taken from Ladefoged. And this is a beautiful depiction, not just diagrammatic. This is actually the sounds articulated, the position of vocal organs based on data from sounds in the middle of the word. The words are heed, hid, head and had, and then had, hod, hod, hood and who would, which means 4 front plus 4 back vowels along the peripheral, peripheral area of cardinal vowel chart. And these are the X-ray photographs of the author, the Peter Ladefoged, when he articulated these English words, American English pronunciation. And what you see corresponding to each one of the configurations is the 2 peaks, the spectral representation of the resonant frequencies. The peaks that you see, F1 and F2 being far apart in case of heed, the short, the long vowel, but the frontmost and the highest position vowel, E, as in heed. You find that the first frequency is the lowest, which is around 250 to 300, and the second formant is perhaps the highest. No other second formant goes that high, and that is about 2500. So it's the ratio should be 1:10, unlike vowel schwa. So like this, the F1, F2 positioning is very, very different and completely dependent on the oral configuration, the nature and size of the air column, the volume of the air column through which the resonance is happening. Now, mapping this articulatory and acoustic parameters. In fact, this diagram itself shows how we are mapping the two. F1 corresponding to large chambers, large first chamber will be smaller, and if it is something like hard, then the 2 columns are kind of equal in size, or the first one is smaller chamber as compared to E. So then that frequency becomes higher. So smaller the chamber, higher the frequency. So then we look at how we map the articulatory and the acoustic parameters. It's very important to understand. In articulatory terms, we consider vowels as front or back, high or low. High or low can be open and close, open vowels and closed vowels, or front and back, E, A as the front vowels and U, O, as the back vowels. Now, if we are able to map these 2 criteria, 2 articulatory criteria as in that cardinal vowel chart that you can see, and define them in acoustic terms, then this is a complete description, more precise description of how high or low, front or back a vowel is. You can quantify in terms of acoustic parameters. So as you can see in this figure, on y-axis, you can see from the lowest point 0 to, it is increasing downwards, F1 values. The first formant corresponds to the vowel height. So more open vowel would mean higher F1 values. Less open vowels or closed vowels would mean lower F1 values. Now look at the x-axis and 0 at the top, and you can see that this is increasing as you move towards your left. You find that you can plot second formant over there, but generally the convention is F2 minus F1 is plotted against F1. F2 minus F1 actually shows how front or back is the vowel. For a very, very front vowel like E, the F2 will be very high, and you deduct F1 value, and still it is the frontmost vowel. Now this is a kind of representation, spectrographic not a spectrographic representation, only the form and frequencies of these 8 vowels put together. A graphic representation, only the frequency scale is used, and you can see that the front vowels have F1, F2s quite far apart as move closer as we move from the high vowel to the lower vowels. In case of back vowels, you are moving, you find that the 2 formants have actually moved closer together, and they move gradually a little apart as we move from, hard, hod, and hood, and who would as the last vowel. So this was also made possible by a series of experiments at Huskins laboratories, and we have mentioned those, and we'll have time to talk about it again. With the help of spectrogram and pattern playback. Pattern playback was the opposite of a spectrogram. You utter a sound and a spectrogram gives you a picture, and you feed that picture back into pattern playback, and the pattern playback gives you the sound. So this is the essence of the 2 kinds of equipments used. In Huskins laboratories, since they had, once they had pattern playback, invented pattern playback, then they could also work with hand-painted spectrograms fed into the machine to get these sounds. And then you work on what particular vowel that sounds like and what particular consonant that sounds like. So these were some of the experiments, which were also, once you produce a sound, you have a spectrogram, then you reduce everything else or eliminate everything else, just pick up those 2 formants, draw them, hand-painted spectrograms, and feed them into pattern playback. It will confirm whether these are the 2 crucial formants for a particular vowel or a consonant or something. So these were also the experiments, done by hand with the help of hand-painted spectrogram. Coming back to this particular picture where 8 peripheral vowels are shown along a frequency scale. The formants are placed along a frequency scale. Now the pattern that you see here is the 2 formants close together, concentrated in a small frequency range, would mean it is a compact pattern. So the back vowels show more or less plus or minus compact pattern. They can be compared with each other, which one is more compact, so plus compact, which one is less compact, so it will be minus C. But the front vowels, they are defined by another feature, acoustic feature, which is plus minus diffuse. The opposite of compact, diffuse, because they are all placed in the F1 in the lower position, F2 in a much higher position. So it is a huge frequency range that they've covered. So E as the most diffuse vowel, we come to less diffuse and less diffuse as we move from E, A, the front vowels. So plus minus compact or plus minus diffuse, they give us 2 important acoustic features based on which you can compare the vowels, you can describe the vowels both in articulatory and acoustic terms. Now back vowels also have energy concentration or formant distribution in the lower range of frequencies. The front vowels are going into very high frequencies. So another acoustic feature is grave and acute. Concentration in the high frequency range, concentration of acoustic energy in the higher frequency range, that leads to plus minus acute criteria, which is important. So plus minus diffuse, plus minus acute will help you define the front vowels much better, and plus minus compact, plus minus grave help you define the back vowels much better. So Apart from this, F1 low versus high can also lead to differences in the timbre or quality of vowels. Now, how does that happen? If it is a vowel E where the first formant is so low as 250 Hz or something, and voice range can be anything up to 300 or 250 Hz, male or female voices. So, the fundamental tone of voice and the first couple of harmonics may also get reinforced if the first formant is too low. So, the timbre or quality of those vowels becomes much more acute and much more sharp. Whereas a vowel like A, which has 800 or 900 Hz as the first formant, there the first few fundamental tone and the first few harmonics have no way of getting reinforced or getting, finding any kind of resonance in this. So, therefore, the quality of those may be very, very weak. The timbre for vowels A or A may not be very clear or sharp as compared to vowel E. Now, analysis by synthesis technique is what I have already mentioned as the experiments conducted at the Huskins labs using pattern playback, where the most important features that you thought were important from a spectrogram, you pick up those features, draw them clearly on a piece of paper and feed that into the pattern playback. It should give you the requisite sound, unless you are missing something from the real spectrogram. So, these experiments in the 60s after the pattern playback, they contributed a lot to our understanding of both consonants and vowels. We will talk about consonants later, but formants for vowels, as you can see, we have mentioned that they were understood much better. Now, formants were also taking different shapes. And these shapes are now important because, as we discovered from those pattern playback experiments and from sounds in a sequence and vowels not occurring alone, vowels occurring vowel plus vowel, two different vowels coming together, or vowel and a glide and vowel and a consonant together. So, in the context of other sounds, speech sounds in a sequence, you find that this is a general guide for what to expect when the sounds are in a sequence. A single vowel with two formants can be steady state formants. The first picture, as you see on the screen. But if you have something like A, two formants are close together, E, two formants are very far, then you start from one position, go over to the other if it's a sequence of A and E together. A, E. You will find the two formants moving apart, starting at one point, moving apart. This kind of a steady change formants are generally for sequences of vowels. Then the third one with a glide. So, here you have vowel E and then a glide and probably ending in a short schwa or a vowel schwa. So, with the year now it is a gradual change formants. It is not a steady change formant, gradual change formants. And the last one, when you have a consonant and a vowel. So, consonant plosion is also there, and after that the vowel formants begin. You find this is abrupt change formants. So, we will see more of consonants in the next module, but for the time being we understand formants can look very different on a spectrogram when they are in the context of other speech sounds. Now, pitch of voice and vowel spectra. This is an important point to mention here. I have shown you some other slides where male voice, female voice and children's voices, the three kinds of voices have different kinds of spectra. And vowel spectra, the formants reinforcement and the spectral peaks can be seen on a spectrum. But the pitch meaning the fundamental tone and overtones or harmonics which constitute glottal tone, that is the source, and supralaryngeal chamber and resonance, what is happening as F1, F2, F3, that is the filter. So, A and B together constitute source filter phenomena for the production of speech sounds. Now, the two seem to be quite independent of each other. A can vary, B may remain the same, B can vary without changing A, which means vowel A or vowel A pronounced by me or you or a third person with different voices, we can still pronounce vowel E, A, whatever we want to say. So, the vowel shapes are determined by the oral configuration which happens after the voice has entered the oral chamber, except for a little bit of change of clarity as I mentioned in this slide. Just look at this slide. The timbre or quality may vary if the first formant is getting slightly influenced by the pitch and the F0 levels. But generally speaking, the two are quite independent of each other. I mean, your voice and my voice, voices may be different, but vowels may be the same. And similarly, the vowels may be different and the voices may be the same, or the other way around. So, vowel spectra for the same vowel in three different voices, as indicated earlier also, you can see the two formants, one at 500, the other at 1500. The peaks are the same, but in between those lines indicate that the pitch of the voice is different. So, vowels with F0 variation, that can be part of prosody, that can be phonetic, that can be phonemic. Phonetic level, it can be vowels with F0 steady, level tone, steady change, it could be rising or falling tones, and then steady state but placed at different levels. You may begin a vowel, you may say like in another language, you may in Thai for instance, or Mandarin Chinese, you may say pa with a placed at different pitch levels, and it will mean three different things. It is level tone but placed 20 hertz higher or 20 hertz lower in the same voice, can be high or medium or low level tones. So, these tones can be phonemic in different languages. So, pitch variations as phonemes, this is the linguistic function, and languages can have pitch levels and contours as phonemes. This we mentioned earlier in case of voice qualities, but you can have vowels as phonemes and you can have a vowel with three different tones as three distinct phonemes. Punjabi has 3 tonal contours as phonemes, Thai has 5 tonal contours and levels, a combination of contours and levels as phonemes, Mandarin Chinese has 4, and F0 can vary across a vowel articulation for phonetic or phonemic function. F0 can also vary across different sections of the sentence, and that is intonation. So, this is the end of our unit on study of vowel sounds, and a lot more research is going on the study of vowel sounds, and also on acoustic spaces, vowel spaces. Vowel space as cardinal vowel chart indicates a certain kind of space, and F1, F2 showing the entire vowel space, that is also important. And lots of studies are still on language specific or descriptions or comparisons across languages using these acoustic criteria. But there is more to come for the acoustics of vowel sounds as we move to the next unit, which is on consonants. We cannot forget the vowel sounds even if we are talking about consonants. So, happy viewing. Thank you very much.